5.3 Conditional Probability and Independence. After this section, you should be able to calculate and interpret conditional probabilities, use the general multiplication rule to calculate probabilities, use tree diagrams to model a chance process and calculate probabilities involving two or more events, determine if two events are independent. When appropriate, use the multiplication rule for independent events to compute probabilities. What is conditional probability? The probability we assign to an event can change if we know that some other event has occurred. This idea is a key to many applications of probability. When we are trying to find the probability that one event will happen under the condition that some other event is already known to have occurred, we are trying to determine a conditional probability. So the probability that one event happens, given that another event, we already know that it happened, so it's already known to have happened, is called a conditional probability. Suppose we know that event A has happened, then the probability that event B happens, given that event A has happened, is denoted by the probability of B given A. So notice that the vertical line you see between B and A, that stands for the word given. It's the symbol we use for given, and it's the second event that's already happened. So you have B, then the slash, and then A. So A is the one that has already happened. So again, we read it as, we read that vertical line as given that. You could also say under the condition that. So what's the probability of B under the condition that A has already occurred? So calculating conditional probabilities, we have the formula to find the conditional probability of A given B. You want to do the probability of A intersection B on the top, and then you want to divide that by the probability of B. And then vice versa, if you switch your B and A, then you still want to do the probability of the intersection of B and A on the top. The probability of A intersection B versus the probability of B intersection A should not be any different. That should just be the part that they have in common for both, for event A and event B. So that's not going to change. It's the bottom of your fraction that's going to change, and it's always the probability of the event that's already occurred, the given part. So notice if you're doing A given B, you have the probability of B on the bottom. If you're doing the probability of B given A, then you have the probability of A on the bottom. Consider the two-way table on page 321. Define events. E is going to be the grade comes from an EPS course, EPS standing for Engineering and Physical Sciences. And then L is the grade is lower than a B. As I was looking at this problem, I kept trying to refer back and call L the liberal arts. So be really careful. I know it's L. I wish they would have called it something else. But event L, it has nothing to do with liberal arts. L is if you've got lower than a B, so you're in the below B column, okay? So find the probability of L, so we want the probability that the grade is lower than a B. So we do want to find some totals, so I'm going to click further and it gives us our totals here. So the probability that you have a grade lower than a B is going to be the 3,656, so those are all the different grades from the liberal arts and the EPS and the health and human services. All of those combined, there were a total of 3,656 that did get a grade level of lower than a B, and it's out of the full 100,000 from the chart. And so that gives us a probability of about 36.56%. So that's pretty simple, but then we get a little bit more complicated. We want to know the probability of event E given that event L has already occurred. So we are guaranteed that we got lower than a B. So what's the probability that the grade is from an EPS class when it's given that your grade was lower than a B? And so there's a couple of different ways you can do this. They're just going to take the green here is coming from anyone who was in the EPS class and got lower than a B, so that's your 800. But notice that they're only dividing by the 3,656 because it's a given that you got below a B. We don't even consider the A or the B grades in the class. So we're not doing it out of 10,000. We're only doing it out of the 3,656. Okay. Another way of looking at it is to use the formula. The formula says that the probability of E given L is equal to the probability of E intersection L divided by the probability of just L. I took it from the previous slide. Instead of A's and B's, I just replaced everything that was an A with an E and replaced everything that was a B with an L. And so I'm breaking it apart for you like this because in the future, you may not have the individual data like you're seeing in the chart here. They may just give you the individual probabilities, and you have to know how to plug them into the formula to get your answer. Okay, so the probability of E and L would be 800 over 10,000. So this is where the intersection is. The 800 is everybody who was in EPS and got below a B in the class, so it's 800, and then it's out of the total 10,000. And then on the bottom, we did the probability of just L, L being that you got below a B in a class. So that's your 3,656. My little calculator screen here is covering it up, but that's this number here divided by the 10,000. And so you'll see my calculator screen. I went ahead and plug this entire thing in here just to show you that you do get this answer here, the 0.2188. So about 21.88% of students, given that they did score below a B, would have been in the EPS class. Yes, the way I did it is much more complicated, but again, sometimes you're not going to have all this individual data to go off of, and so you're going to have to be able to plug into the formula, and you see that you can get the same answer. So now they're going to switch it up on us, and so now they want to know what's the probability that you got a grade that was lower than a B, given that you were in the engineering and physical science course. So lower than a B, given that you are in the EPS class. So they simplified it. They did the intersection of both, which is 800 again, but now they're going out of the total that were just in the EPS class, so that's 1,600, and so when you divide that, it's 0.5. Doing it the much more complicated way, I would do, again, I switched every A, made it an L, and then switched every B and made it an E from our formula. And then I did the probability of L intersection E. Notice that it's still 800 over 10,000 because E intersection L is the same thing as L intersection E. Where it changes is on the bottom here. Instead of dividing by the probability of L, now we're dividing by the probability of E. Remember that E is that you're in the EPS course. So for all the students, the probability that you're in the EPS course is 1,600 out of 10,000. And so I took this mess here, this fraction, and I plugged it in up here in my calculator, and you can see that it does match the answer they gave us of 0.5. Okay. The general multiplication rule, the probability that event A and B both occur can be found using the general multiplication rule that the probability of A intersection B, remember that intersection does mean and, is equal to the probability of A given the probability of A times the probability of B given A, okay, where the probability of B given A is the conditional probability that event B occurs given that event A has already occurred. So again, the second letter is the one that's already occurred. So in words, this rule says that for both of two events to occur, the first one must occur, and then given that the first event has occurred, then the second must occur. The general multiplication rule is especially useful when a chance process involves a sequence of outcomes. In such cases, we can use a tree diagram to display the sample space. Consider flipping a coin twice. What is the probability of getting two heads? So if you flip it one time, your possibilities are heads on your first toss or tails on your first toss. And then when you go to flip it a second time, if you got heads on your first toss, then your second toss could be a heads or a tail. But if your first toss was a tail, then again, your second toss could be a heads or a tail. So hopefully the tree diagram makes sense to you. They want to know the probability of getting two heads. If you've drawn the sample space, let me get the highlighter here. If you've drawn the sample space, then you can see that the only possibility of having two heads is getting a heads on your first toss and a heads on your second toss. So it's truly only one out of the four possibilities. Okay, you've got to follow the branches. So we could have gotten a heads with a head, We could have gotten a head with a tail, we could have gotten a tail with a head, or you could have gotten a tail with a tail. And so just counting there, you can see that it's 1 out of 4. The other way of looking at it, though, is the probability on your first toss is 1/2 to get heads, and then the probability on your second toss is 1/2 to get heads. So if you multiply those together, you still get 1 out of 4, so 1/4. The Pew Internet and American Life Project finds that 93% of teenagers ages 12 to 17 use the internet, and that 55% of online teens have posted a profile on a social networking site. What percent of teens are online and have posted a profile? So again, they're going to do a tree diagram for this for us. Hopefully all these numbers make sense to you. Let's kind of walk through it a little bit. 93% are on the internet. So if 93% are on the internet, then it should make sense to you that 7% are not on the internet. So you either are or you are not. So if we know 93% are, then that leaves 7% to be off of the internet. Remember, your probability does have to add to 1. So if we do 1 minus 0.93, it tells us this 0.07 is left over, okay? And then it says, of the ones that are using the internet, 55% have this profile on a social networking site. So if they're on the internet, 55% of them do have a social network profile. So that leaves us with 45% that do not have a social network profile. Okay, if they're not on the internet, guys, then they can't have a social network site. So that's going to be 0 for them having a profile, and 100% of them that are not on the internet, 100% are 1, probability is 1, that they're not going to have a social networking profile. Hopefully that makes sense, okay? So the probability that they're online is 0.93. The probability that they have a profile, given that they're online, is going to be 55%. And I talked to you about how that, came about. So now we want to know, what's the probability that they are online and they have a profile on the social networking site? So the formula for that is that we're going to do the probability that they're online, which is 0.93, times the probability that they have a profile given that they're online. So we're going to be multiplying the 0.93 times the 0.55. Okay, so you can see that about 51.15%, if they're online, are also going to have a social networking site profile. So they say 51.15% of teens are online and have posted a profile. When knowledge that one event has happened does not change the likelihood that another event will happen, we say that the two events are independent. Two events A and B are independent if the occurrence of one event does not change the probability that the other event will happen. In other words, events A and B are independent if the probability of A given B is equal to just the probability of A, and then the probability of B given A is just equal to the probability of B. When events A and B are independent, we can simplify the general multiplication rule, since we know that from above, the probability of B given A is equal to probability of B. So I want you to recall from previous slides that it said the probability of A intersection B is equal to the probability of A times the probability of B given A. But it said that the probability of B given A is equal to the probability of B, so you can replace that in the formula, and so you've simplified it a lot to just say that the probability of A intersection B is equal to the probability of A times the probability of B. And again, that only works if the events are independent. So if A and B are independent events, then the probability that A and B both occur is equal to the probability of A times the probability of B. Following the Space Shuttle Challenger disaster, it was determined that the failure of O-ring joints in the shuttle's booster rockets was to blame. Under cold conditions, it was estimated that the probability that an individual O-ring joint would function properly was 0.977. Assuming O-ring joints succeed or fail independently, what is the probability all 6 would function properly? Okay, so we would look at each one independently. So we want to know the probability that joint 1 is fine, the probability that joint 2 is fine, joint 3 is fine, 4 is fine, 5 is fine, and 6 is fine. So we want to know all 6 of them, and it is and, so that's going to remind us that we need to multiply these individual probabilities together. And they are independent. If joint 1 is bad, that has no effect on whether joint 2 is bad or good. They're independent of one another, okay? So by the multiplication rule for independent events, the probability would be the probability of joint 1 being okay times the probability of joint 2 being okay, all the way through the probability of joint 6 being okay. So each one, it told us that they would function properly 0.977 per, 97.7% of the time, if you will. So each one has a probability of 0.977 for functioning properly. So you want to multiply that together 6 times. I don't know about you, but I like to shorten things as much as possible in the calculator. So instead of typing all this out and risking the possibility of me typing in something wrong, I just went ahead and did 0.977 to the 6th power. Notice that does, when you round it, does give you the same answer. So shorten things for yourself if you can. We should know that multiplying something by itself 6 times is the same thing as raising it to the 6th power. Okay, so there's an 87% chance that the shuttle would launch safely under similar conditions. So there was a 13% chance that it would not launch safely because 13% of the time, at least one of the joints would malfunction. So in this section, we should have learned that to calculate and interpret conditional probabilities, remember again that conditional probabilities are finding the probability of something happening given that something else has already occurred. So we've got that second event that we're depending on. So that's why it's called conditional probability. We use the general multiplication rule to calculate probabilities. So generally speaking, we can multiply the probability of 2 events together and then use tree diagrams to model a chance process and calculate probabilities involving 2 or more events. We will see tree diagrams used again in our practice worksheet with a little bit more complicated problem than just flipping coins and then, kind of similar to what we saw with the using the internet and then the social network profile example that they gave us. So something similar to that, you'll see the tree diagram used again. And then determine if 2 events are independent, and then when appropriate, use the multiplication rule for independent events to compute probabilities. So here it's simplified a lot more. We don't have to worry about any given stuff. We're just going to do that it's the probability of A times the probability of B.